So, yeah, we may begin just to be a bit on time. So, good evening, and thank you everyone for coming to our seminar series of GSPP. So today, as you see in the title, that's going to be a Zoom discussion, and we're going to have like our honorable guest, Dr. Brun, that will talk about the mental additive for manufacturing of value chain. Few words, and Dr. Brun has also a short bio slide that's going to talk about his professional experience. So Dr. Brun is a faculty at the Duke University and Sanford School of Public Policy and research director of E4 Carolina since 21. And that's an energy industry association. His research area is global value chain analysis, focusing on energy, environment, and economic development at the international, national, and local levels. Yeah. So, Dr. Brun, the floor is yours.
Thank you, Dean Zanarias, and thank you all for spending a little bit of your evening with me. I wanted to talk today about the metal additive manufacturing value chain. And just before I get started, wanted to gratefully acknowledge that this research was funded under the target program for the project entitled Additive Production Systems and Metal Powders for Kazakhstan Industry by the Ministry of Industry and Infrastructure Development of the Republic of Kazakhstan. Thank you for the funding research. A quick agenda. Want to do a quick introduction, talk a little bit about the theoretical framing and relevant literature for global value chain analysis, and then wanted to dive into the metal additive manufacturing value chain, and then talk about kind of what I came out learning as a scholar of value chain analysis and things that surprised me in the industry and next steps. Very briefly, this is essentially part one of a two-part study. I will be presenting the global value chain of additive manufacturing and particularly metal additive manufacturing. Sometime in the spring, Professor Howie will be talking about how Kazakhstan is currently positioned in the value chain and what upgrading trajectories could look like for the country. So very quickly about me, I'm a value chain specialist, currently the director of research at E4 Carolina's Energy Industry Association. I'm an adjunct professor at the Sanford School at Duke University, where I was in the past a research analyst and project manager, including projects in Kazakhstan from 2009 to 2018, and you see my credentials there. So I wanted to open up the conversation with providing a theoretical framework for understanding additive manufacturing. So the theoretical framework is global value chain, and that is a theoretical framework that came out of economic sociology. And has, of course, natural alliances and interests in business, particularly in supply chain logistics, but it did originate kind of as an independent area of scholarship. So just to define our terms, value chain describes the full range of activities that firms and workers carry out to bring a product from its conception to its end use and beyond. And the and beyond part is rather important, particularly as we think about the environmental footprint of products. To have insights into how that product finalizes its disposition and ways to dematerialize that product makes it, rather than a linear process, it makes a full circle process. And so there's two core concepts value chain analysis. One is governance, and there's basically two types of governance. One is firm governance, which questions along an industry who drives the specifications that others must produce to. And the insight very early on, and I guess this is in the 70s, was that it's producers, it's original equipment manufacturers that drive, in most cases, the specifications that others have to produce to, and also regulate how the value chain is conducted, who gets to go in, who stays out. In the 80s, and particularly in the early 90s, in the academic literature, the rise of global retailers really changed who drives governance in a lot of value chains. So it moved from producers in some areas of industry and commerce into buyers or global retailers. So when you think about textiles or other consumer products, it's the global retailers that really matter. So global retailers in the United States would be places like Walmart, Kmart back in the day. It's Costco. It's those types of JCPenney, Sears, all of these companies that have a direct face to the consumer. And that change from producers to buyers was really captured in 1994 in this book called Commodity Chains and Global Capitalism. There's also supply chain governance, which is how are industry level supply chains organized by lead firms and why. So for example, you have a lead firm, whether it's a producer or a buyer, but how do they monitor and maintain their value chain? Is it a market relationship where its price means that you get included in the supply chain? Or is it more networked oriented, where you have modular, relational, or captive relationships with your suppliers? And the explanatory variables to understand which type of supply chain governance was kind of put forth in 2005 by this article called The Governance of Global Value Chains in the Review of International Political Economy, that identified some explanatory variables for why it is that different industries have different types of supply chain governance. And those were complexity, codifiability, and supplier capabilities. For those of you who are interested or knowledgeable of transaction cost economics, you'll see kind of a close alignment with some of those identifying variables that was put forth in that analysis also. The second key concept is upgrading, which is, okay, how do we get from where we are now as a country, as a region, or as a firm to improve your position in the global economy? For example, you have a capability, you're in the value chain, but you would like to improve your products. You want to go from a low value added product to a higher value product. How do you do that? Or you find more efficient processes, or you want to go from one link of the chain into another link of the chain. How is that possible? So this upgrading piece of the framework really analyzes different types of strategies and what the likelihood is of success to move into those upgrading strategies. And so the value capture is really about where, what part of the world are you doing it, and what part of the segment are you doing it in the value chain, and who's doing it. And the who is really an important part of the value chain analysis, because ultimately activities are conducted by firms. And so understanding the global reach and extent and product portfolio and capabilities of those firms is very important to understand the opportunity for value capture. And the upgrading by countries or regions is really driven by the activities of firms located within their borders. And so understanding what companies you have in the region or in your country to participate in the value chain is also a first step of the analysis in order to understand both upgrading and governance of the value chain. And we'll see here that governance and upgrading are linked. If governance is very tightly controlled, the upgrading opportunities are very different than if it's a market where price matters the most. So that's the theoretical framework. It's been worked on, I guess, since the early 90s with legacies all the way going back to the 60s and 70s. But it's been applied to a lot of different areas and topics that I'll present in future slides. A second part of this, and why am I here talking about additive manufacturing is that I wrote with Gary Gireffi and James Zahn of UNTAD an article about the lightness of Industry 4.0 lead firms. Additive manufacturing ultimately is part of this kind of revolution of industrial production. And so in this article, in case you are interested in reading it, talks about the changing nature of production in global value chains, the effects of digitalization on global value chains, both the supply chain effects, but also the rise of new lead firms. Think of Alibaba, think of Amazon, that suddenly are arising as a result of being able to do industrial production in a different way. And so we investigate kind of the characteristics of a digital economy and then provide 3 scenarios for digital transformation in global value chain lead firms. And so today we're talking about a portion of this, which is additive manufacturing. So just briefly, in terms of the major components of the framework, there's an input-output structure, which is basically a linear diagram showing pre-production, production, and post-production activities. The geographic scope, where are the firms? Is it local? Is it global? Who are the lead firms? What are the governance structures? And what are the upgrading opportunities? And then the institutional framework. What are the rules, forms of exchange, and key organizations that help us understand the value chain and are really important to the conduct and performance of the value chain. So in analytical sections, when we write reports on value chain analysis, we'll have an area where we talk about the global value chain, we map the value chain, we talk about geographic distribution, we talk about lead firms, governance and upgrade trajectories, standards and institutions that are important to the value chain, and a final part, which isn't part of the original framework, but I think increasingly is in the literature, which is that human capital and workforce development are essential to understanding upgrading opportunities in the value chain. If you don't have the workforce, if you don't have the people capabilities in order to perform in value chains, it's very unlikely that you will have success in either entry or upgrading in a value chain. And so human capital and workforce development is increasingly becoming important in the literature to understand upgrading. Really quickly, just some representative GVC projects. You see here some projects in bold that I've worked on. Most recently, I've worked on a lot of renewable energy projects, but also traditional energy projects. But in the past, I've worked both in low tech, medium tech, and high tech. And that's a real benefit of this framework, is that it provides kind of a framework to understand industries and whether those industries are low tech, located in a remote part of the world, or high tech and located in a near part of the world. The framework is suited to be able to understand and to provide some policy relevant recommendations about upgrading. Here's just a map of some of the projects, of the footprint of the projects that we've done at Duke and others. And so now I want to change from kind of the value chain framework to what I was asked to do to understand additive manufacturing, the global value chain of additive manufacturing. So I provided in my draft report an industry overview that has the industry definition, an understanding of trade, who is importing and exporting items and portions of the value chain. And then I've focused on the meta additive manufacturing value chain. Metal is a portion of additive manufacturing. You can do it basically with plastics or polymers or with metal. I focused on the metal portion where I provide kind of the map of the value chain, the input-output structure, and identify some global lead firms. And so with your indulgence, let me go through some of my findings of my research. So first, what is additive manufacturing? Additive manufacturing builds a three-dimensional object by adding successive layers of material to it. If you think of it as depositing material layer by layer that is organized by a computer-aided design with material that builds up that product is how additive manufacturing occurs. It's very different than where you have a bar of metal, for example, and you're carving it, you're milling it, you're shaping it in order to meet your specifications. So it's not subtractive. It's also not formative in the sense that there are no casts or molds in order to create your product. You're doing it one by one based on a design. And so there's different types of additive manufacturing. There's at least these types that you see here on the screen. That polymerization, photopolymerization, was the first additive manufacturing technique. It basically uses liquid light-activated plastics in a vat, in a bucket, essentially, or a bin, that gets hardened by the use of light. And then you build up the material or the part that way. You also have powder bed fusion, which is really the second type of additive manufacturing technology that came into commercial application. And there, thermal energy, whether it's a laser or an electron beam, bonds a powder that layer by layer. And so it uses high energy to essentially melt that powder in very specific ways to build up the part. There's also material extrusion, which is an increasingly interesting application where you have a slurry of material, and then you basically are extruding, you're pushing out that material in a very precise way that's controlled by computer-aided design to build up a part. There's others. In terms of which ones are most important for metal additive manufacturing, it's really the powder bed fusion technology that is the most important. Although there are material extrusion, binder jetting, and directed energy deposition applications for metal, but powder bed fusion currently is the most commonly applied. Really quickly, I wanted to provide the audience an example of the different types of metals that are used in additive manufacturing and some kind of concrete examples. So essentially, you can use steel to create spare parts, and here are some examples. Steel is commonly used in manufacturing, and so the ability to produce individual pieces that have characteristics that are helpful for the development, either the prototype of a part of a product or production part is very helpful. You can also use aluminum or aluminium if you're in England, and you use those when steel doesn't work because you need lightness or corrosion essential, or where weight is essential. And so here on the right, you see a spare part that is printed by Mercedes-Benz using aluminum. You can also use titanium and titanium alloys. There on the right, you see a landing gear beam that is 3D printed with aluminum alloy. You use titanium in high performance applications where weight is also important. There's three additional kind of categories: cobalt chromium, which is used in kind of medical prosthesis, both for orthopedics, but also for dentures. And so here on the right, you see an example of how cobalt chromium was built up in order to produce basically an odontology fixture that is going to be used in a mouth. So this is a dental implant. You can also use nickel. Nickel is particularly used where you have high heat and you need strong corrosion-resistant metal. Here you have, in the picture, you have a aerospike nozzle, which is a type of nozzle that's used in aerospace. And then you can also print jewelry, which was kind of attractive when I first came into this field. Oh, wow, instead of having to have a goldsmith create pieces, you can essentially print them out, and you can do so with unique, thin, and intricate designs, which is one of the applications and characteristics and benefits of additive manufacturing. I'll note that while precious metals are primarily used for jewelry, there are some aerospace applications, in particular for platinum. So what are the pros and cons of this technology? The core benefit is that it provides agility to a manufacturer. It makes prototyping very easy. You can iterate the design. You don't need a lot of production in order to be able to reach economic scale. And so the prototyping is very much why additive manufacturing became applied into manufacturing value chains. It simplifies complexity. You can change characteristics of your product very easily, and it makes that kind of that design production iteration very simple. You can also reduce manufacturing cost and waste. We spoke briefly about how value chains also think about the and beyond part. Well, you can design it, you can design products where they have low material requirements at the beginning. And so reduce cost and waste because you're essentially building up a part and not taking product away from a part to create it. Really does achieve some of those environmental goals and also just economics for reducing waste and the associated costs for production. You can use additive manufacturing for what's called mass customization. If I want a pink tennis shoe or a yellow tennis shoe with gold stripes on it, I can tell my tennis manufacturer that's what I want, and it's something that the tennis shoe manufacturer can do very easily. There will be charged a premium for it, but you can do that. It's possible to do that. Or if someone in the aerospace industry wants a particular type of additional component or color or size, that's also easy to do. Reduced inventory. If you're printing parts on demand, you don't need to have a large storage of inventory in your back. You can just print them as you go along. And in particular, if you have machinery that is no longer in mass production, you can create those legacy parts, the one-offs, in order to keep the machinery working. But you don't have the mass production that it had been in the past, and so legacy parts are important. Hybrid manufacturing. You can combine additive manufacturing with traditional manufacturing methods. You can create molds, for example, using additive manufacturing, and then use your traditional casting method in order to produce a part. It's also distributed. An opportunity for production in remote places. Rather than having to ship the good from one place to the other, you can produce it where the demand is. And so that's a real benefit for additive manufacturing. There's also some downsides. Production volume and scale. You don't achieve the economies of scale in additive manufacturing that you do in normal production processes. It costs just as much to produce one as it costs to produce 100 generally, and so you don't have the declining marginal costs of normal mass production. Quality control and product certification currently is a challenge. Each part has to be looked at and to make sure that the production process is in place in order to achieve the precise specifications that is required by a manufacturer is important, but it's also difficult to achieve particularly if you don't have the workforce. There's also post-processing costs. Typically, particularly in metal, you'll have between 40 to 80% of the time spent in post-processing, adding finishes, making it look the way you want, taking off the matrix that it was used in order to build up the additive manufactured part. There's also business case challenges. When you talk to original equipment manufacturers, they say, well, why should I use a 3D printed part when I've been doing it this other way in a perfectly fine manner? And so the adoption of this technology really becomes selling that original equipment manufacturer that you can do things with additive manufacturing that you couldn't otherwise do, or achieve some other benefit to the business in order to adopt that technology. And then, as I mentioned, there is a lack of skills and personnel availability. It's a highly technical area of production, and those skills and personnel that can do it, particularly do it well, are not available everywhere. So let me talk a little bit about kind of markets of additive manufacturing. So currently, it's about a $20 to $23 billion global market. There's a range there because COVID really did interrupt the trajectory of this industry in terms of growth. And metals make up about 20%, 18% of the market. You'll see that plastic powders, whether they're polymers or photopolymers, really are the majority of the market for additive manufacturing. So the next part of the report investigates trade, and given the amount of time that we have available, I will go quickly through the trade analysis. But the report looked at mineral reserves, mineral production, and mineral trade for the major additive manufacturing metal powders. What we saw, what I found is that Kazakhstan in particularly has a lot of reserves and a lot of, but not a lot of production. So it's when you see that Kazakhstan has almost a 40% share of global reserves, it only has 17% of global chromium production. South Africa dominates, and interestingly enough, Turkey in terms of chromium production. When you look at the exports and imports of chromium, you see that the major export producer for chromium powder is Russia, followed by France and the United Kingdom, and importers are the US, Germany, and Japan. And you see, if you're interested in this report, you can see it broken down for each of the metal powders that were analyzed. Also, there's a couple of kind of takeaways that China really is a major player in this portion of the raw commodities, or what's called feedstock in the industry, portion of the value chain. And for those, they typically have over a 70% share of imports. And the implication is that if you're tied to China in terms of your imports and exports, you're also tied to their kind of position and upgrading in the global markets that they participate in. And that processing and export of metal powders are conducted by advanced industrial countries, not the raw mineral producers. So what typically happens in these powders that are used in additive manufacturing is that the production of the material comes from one place, but then the powder production, creating the specific powder that's needed in additive manufacturing, comes from another country and then is exported to a third country. And so there are potentially some interesting upgrading opportunities to move away from just being a raw materials producer to being a powder producer. And I also looked at the trade in additive manufacturing machines. The HS code for this is currently in play. What we have currently in the trade statistics just uses all additive manufacturing machines. It doesn't separate between polymers and metal machines. But you see that the exporters, according to Comtrade, are Germany, China, and Italy, and importers in terms of majority are China, US, and India for these additive manufacturing machines. Next, I want to talk about the value chain. And so one characteristic of these value chain reports is we always have a value chain map. It basically moves from raw materials or feedstock into production and then post-production. And so let's talk a little bit about the value chain for metal additive manufacturing. So you have here on the top, you have the major segments: raw materials, materials processing, components and manufacturing of the equipment to produce additive manufactured goods, post-production services, and then the end markets that are ultimately the demand drivers for additive manufactured parts. In each segment, there are subsegments. So you see that there are metal and alloys that are listed here in the raw materials, the materials processing that's required in order to move from a raw material feedstock into something that can be used in an additive manufacturing machine. You have some components. You have a lot of software, interestingly enough, that is part of the additive manufacturing value chain. And then, of course, you have electronics and balance of plant in order to kind of house the printer. You have these different types of printers, right? We talked about binder jet printing. We talked about powder bed printers. And so these are the different types of printers that are available in the market. Then you also have post-production services. And these are actually a really important part of the value chain, making sure that the part is of a quality that's needed, making sure that in terms of the post-processing systems that it meets the specifications and requirements of the end user. And it also includes material recovery. As you're building up a part, some part of that powder gets lost or is cast off by the production processing, and being able to recover that material and to combine it with what's called virgin material and then reuse that material is very important. And then you see the end markets here. The end markets are, aerospace, automotive, industrial, medical, and then other, which are listed here. Consumer and retail are things like, tennis shoes, although that's not the metal portion, but jewelry would be an example of the consumer retail side. You have energy that requires, for example, oil rigs, require a lot of pieces and parts. There are pieces of that can be produced by additive manufacturing, as can for nuclear power plants. And then construction, you can use additive manufacturing in place for construction. Below the kind of segments and subsegments are production support services. And these are places where are supporting the value chain. So these organizations called service bureaus are essentially print farms. So they have, if you think about server farms, it's just a stack of servers in order to capture data. Well, in this case, it's stacks of printers that produce to the specification of the end market consumer. And so they're essentially taking the computer-aided design, they're printing it for you. They might even do some of the post-production services and then send it to the end market user. There's also value-added resellers, and these are usually local, national firms that purchase equipment that advise end market users about how additive manufacturing can be used in their production process, and really work almost hand in hand with the end market original equipment manufacturer in order to make sure that that particularly 3D metal printed part meets the specifications and can be useful for that end user. And then there's the supporting organizations and institutions. There's policies and regulations that are important, increasingly important in terms of additive manufacturing, trying to set standards, production process standards, and metal powder standards in order to really propel this industry into the next level of adoption by original equipment manufacturers. There's also training, governments, and non-government organizations that are active in this value chain. So next, I wanted to provide kind of an overview of some of the analysis that was done in the report. For each segment, I created a table that has the segment, the particular subsegment, a description, and then the harmonized system code that's used to understand import and export activity in this portion of the value chain. So in the report, you'll see this listed for each segment. You'll also have companies that are active in each segment. So here for metal powder manufacturing, you have some of the major companies that are active globally in the production of metal powder. You see some companies like ThyssenKrupp or Rio Tinto. Those are major international companies that also produce metal powders. And so that's in the report. Supplementary to the report, I also provided a list of companies, global companies, in each segment of the value chain with the name, a description, if I could find it, the number of employees and annual sales, the codes, the industry codes, and then the headquarters and branch locations for companies that we were able to identify that were both either in Kazakhstan or in China. And so that is a supplement to the report. Let's talk a little bit about industry governance, because again, governance is one of the key components of the value chain framework. And so my takeaways is that this is very much a producer-driven lead firm governance value chain. The adoption of the technology of additive manufacturing really depends on selling the end market product manufacturer that has benefits. And that is almost on a part-by-part basis and relationship with the product manufacturer. The low-tech versus high-tech markets appears to be a critical factor in supply chain governance. In the low technology, so you can print everything from screws and nuts using 3D additive manufacturing, but you can also do very high technology things. And in the high technology areas, it's performance, it's durability, it's weight that really are the key drivers for competitiveness. Whereas in the low tech, it's really the unit costs. And so you have different governance structures. In the low technology side, you have more of a market governance. And in the high technology area, you have more of a network governance. It can even be captive, where you have a sole supplier for a type of product or even a component that's used particularly in aerospace. And so the implications are that for the high technology areas, trust, experience, supplier, and part performance is really important to supply chain entry and upgrading trajectory. So I want to conclude my comments with some of the kind of the things that I learned as a researcher and some surprises. So what I really was surprised by was that additive manufacturing can complement traditional manufacturing rather than supplant it. When you talk to manufacturers about additive manufacturing, they say it's wonderful, but only in a piece or a portion of my product's value chain or supply chain. And so it really is being used currently as a complement to traditional manufacturing rather than a substitute for it. Early on in the literature, it was thought that it would revolutionize how things were produced and that things would be essentially all be 3D printed. That's not the case. Traditional manufacturing continues and it's being supplanted in certain pieces, certain parts of a product with additive manufacturing. Another surprise is that, and this was referred to in previous comments, is that the countries that are really the mineral reserves and producers of the minerals and metals that are used in additive manufacturing are very different than the ones that export the metal powder. And so in terms of value added, you could really think about how do you move from just being a producer of that raw material into being a powder exporter, and how do you bring the companies, the lead firms, into your country in order to help that process of upgrading from just being a raw minerals producer to being a powder exporter. Post-processing in additive manufacturing takes a lot of time. Again, the literature says it's between 40 to 80%, depending on the type of metal that you use, the type of manufacturing technology that you use to produce. And it just takes a lot of time. And so that is a downside for additive manufacturers and the adoption of additive manufacturing into additional supply chains. There's a wide range of technology and product markets. There are printers for everything and for every production use. If you're printing one part at home versus printing 1,000 parts in a business, there's a wide range of capabilities and manufacturers of printers that can suit that need. Metals are still an emerging application. Photopolymers and polymers more generally are what 3D manufacturing, 3D additive manufacturing has been focused on. But the metals piece of it has an extraordinary trajectory and potential because there are so many things that use metal in the manufacturing processing. And so it's still emerging, but there's a lot of potential applications for it. The production support piece of the industry is actually quite dynamic. Print shops are, necessary in order to produce the product, but these value-added resellers appear to be key actors in being able to show end markets that additive manufacturing is the way to go for a particular component, for a particular part in their supply chain. And so these value-added resellers also often have consulting arms of their activities, and so they are a pretty important piece of the value chain. Centers of excellence in which countries and product manufacturers of the 3D printers work together to show industry how additive manufacturing can be used in their particular application are very important. And currently, they're located all around the world, but they tend to be clustered in Western European countries, in China, and in the United States. Again, an insight that I referred to in the past was that adoption depends on selling end market product manufacturers its benefits. And then ultimately for Kazakhstan, and this is really going to be in part 2 of the analysis that will be done in the spring, is that for Kazakhstan, you need to think about the competitive niche and upgrading trajectory that Kazakhstan can play in. Chromium powder, just as kind of an aside, has some interesting possibilities. But it needs to be analyzed carefully to see whether it is an opportunity for Kazakhstan to play in that piece. So with that, I will end my comments. Please get in touch if you would like to follow up. Here is my contact information for my role as research director of E4 Carolinas. And with that, I turn it back over to Dean Zanarios.
Great. Thank you, Dr. Brun, for the presentation. We took quite the flavor of value chain, but what I have to confess that I'm quite ignorant of the topic, and I learned quite a lot. So please, Q&As, we have like 10-15 minutes. You can raise hand, as Damira has mentioned, or you can chat. Yeah. Any of you have any questions that you would like to hear some more information? Yeah. Okay. By the way, I'm Vice Dean for Research, so this is the real Dean. So, when that, please.
Thank you, Professor Lukas, for that very interesting talk. I was just wondering the use of the term global value chain. Is it appropriate for additive manufacturing? Because it seems like we are going back to traditional manufacturing, where you have a standalone manufacturer using resources or parts to produce a final product, as opposed to the global value chain that we know of, where you have networks of producers across national boundaries that brings different parts together, and you have a final product. That's the first question I had. The other question I have is, you mentioned about the importance of personnel and skills. What specifically are the skills that are required to, to have a viable AM or additive manufacturing base for a country? Take the case of Kazakhstan. I mean, Kazakhstan has a lot of reserves, but it doesn't produce the metal powders. I presume it doesn't have a lot of additive manufacturing taking place. So if you were to have a recommendation for Kazakhstan to make use of the chromium reserves and to have some kind of additive manufacturing base in Kazakhstan, what kind of advice would you give to the people who are involved in aviation policy, for example? First two questions, and maybe I'll have other questions later on. Yeah.
Thank you. So on your first question about the global nature of this value chain, the production, the end market production continues to be global. And what's interesting is that current analyses of how additive manufacturing has affected the extensiveness of value chains shows that it continues to support this global trade that we've been experiencing, I guess, since the late 80s. There's been a couple of studies that I've seen, one done by OECD, the other by a group of researchers, I believe it was out of Germany, who analyzed quite carefully about the extensiveness of the value chain for several products. And we're actually surprised by that while the printed part, it gets included into that final good, but that final good can be sold all around the world. The other portion that's global is that if you think about just the amount of trade that occurs from the raw materials side in order to get shipped and turned into powder, that is an international footprint. The producers of the software and the components that go into the printers is also traded goods. And the printers usually get shipped from one country to another country. So that is also international trade. And so I expected the same as you, that suddenly we go from a global production system, or at least regional production system, down to a very localized production system. But the evidence has borne out, at least from these early studies, that additive manufacturing supports global trade rather than supplants it. To be determined, but that's at least the early evidence. On your skills question, a very good and insightful question. When you get to the high technology areas where additive manufacturing applications are required, those specifications are unique to either a particular part or a particular industry. And those parts have to be produced to those standards. Getting additive manufacturing to be able to be included in those highly classified end markets, aerospace, shipping, example, or energy production, is really place where the classification society, the workforce the workforce trainer, and these value-added resellers working with the printer manufacturers really provide a nice coalition of interests in order to make sure that that product meets the specifications. That's why those centers of excellence that I mentioned are so important, because they're able to house, they're able to be the kind of the node, the central part of the network for all of those people and activities and organizations to get together in order to make sure that their part is suitable for adoption in the end market. There are, in terms of expertise and your specific question about what Kazakhstan can do, my recommendation on this piece would be to talk with the classification societies. There's two organizations that are active in the specifications piece. ASTI International is one of them. And there is another classification society that's very active, that's in the report. And I would almost take up, my first step, if I was Kazakhstan, would be to talk to those organizations and say, we have a demand for 3D printed products in our country in XYZ industry. We need to better understand how we get additive manufacturing to be included in those supply chains, and to develop the workforce, the quality control mechanisms, both on the material product side, but also on the post-production side, in order to achieve those specifications.
All right, we have room for 1-2 more questions, if there is any other. Or consider it a bit too late for our...
Well, if there are no further questions,
please,
I may follow up by that. You mentioned that additive manufacturing is only a complement to traditional manufacturing, right? So the role it plays is not, if I understand, it's not the large-scale additive manufacturing of parts and so on. But do you foresee additive manufacturing going the way of mass production? I mean, and if not, then what are the constraints, whether it's technology, whether it is the machines and so on? Do you foresee a future where you have mass production of additive manufacturing parts?
Thank you for letting me clarify that comment. Additive manufacturing can support traditional manufacturing in terms of being able to produce the casts that are required, and it can support current technologies and mass production. And just to be clear, there are 3D printed parts that are mass produced. There are screws and nuts and bolts that are used, that are 3D printed all the time. And so mass production does occur with additive manufacturing. It's at an industrial scale. And so there are pieces of it that are mass production. And so the future is here, in particularly the low technology areas. So if you think, I mean, the specifications for bolts and nuts and gears just aren't that high. But when you get into rocket nozzles, those specifications are very high and very difficult. And so it's that difference. It's between, currently mass production is in the low technology areas. In the high technology areas, it's very much customized production. And I don't know if it will get past that, just because of the nature of those industries that are, very, very customized and require very detailed and high specifications in order to be competitive in. So yeah, I think there are portions that are mass produced and will continue to be mass produced, but in some particularly high technology markets, it will continue to be kind of one-offs, detailed, where you're changing a little bit, right? So let's say that you're building airplane seats. You can build airplane seats with aluminum using traditional manufacturing approaches. Or you can use additive manufacturing. The benefit is that the additive manufactured component is stronger, but it's also about a third less weight than the traditional manufactured good, because you can carve out metal that you don't otherwise need with the specific design, that a computer-aided design. And so if you think of mass production as mass production for airplanes, you know, you can build those airplane seats over and over again using 3D printed approaches. But, you know, we're still talking about pretty low numbers rather than the high numbers in low technology areas. So let me thank you again for letting me clarify, because I don't want to leave the audience thinking that this is just a one-off, you know, prototyping sort of activity. It is being currently used for mass production in some areas.
Great, thanks. And I also see in the chat that we also have some kind of initiatives also in Nazarbayev University. Thanks, Professor De La Mora, for mentioning this. Yeah, all right. And Dr. Brun, I hope that we're gonna continue some cooperation with GSPP and you, and we're gonna have like some other talks in the near future.
I would enjoy that. And thank you again for the invitation, and to Peter and to Didier to allow me to do this research. It was fun. It allowed me to continue my connections with Kazakhstan, and I thoroughly enjoyed it.
Great, great. Thank you all, and have a nice day for you and nice evening for the rest. Okay, goodbye.
Thank you very much, Lukas. See you soon.
Bye.
Bye-bye.
Bye.